Thank you. And then we proceed to the next speaker, being Professor Cengiz Toklu, and he will talk about the use of cable-strut structures on space bodies. And Professor Toklu is a civil engineer from Middle East Technical University in Ankara, Turkey. He has studied in Université de Pierre et Marie Curie in Paris as well, and done a fair bit of work on finite element methods of nonlinear structural systems. And he is one of a few, well, it's getting more and more now, but producing simulants of lunar soils as well. So please, Cengiz.
Thank you, Niklas. I'm trying to
you are
share the screen. Is it okay now?
It is visible, yes.
Okay, thank you very much. And thank you for having me here. I will talk about today cable-strut structures that can be used on Moon, Mars, and other space bodies. Okay, I will talk about, general principles, design and analysis of these structures, loads acting on these structures, material properties, and we will talk about these structures in general. Now, as the name indicates, cable-strut structures are formed by cables, struts, and I'm not seeing all the screen. Okay. Of course, if we have a structure like this, there are many other types of structures that can be used on Moon and Mars, etc. Like, for example, we can use bricks or concrete or, 3D printing of concrete, etc. They all have their advantages and disadvantages. So today we are, in this speech, I will talk about these cable-strut structures. They are, of course, formed by cables and bar struts. The struts are to carry compressive forces, and cables are to carry tensile forces. There may be press stressing in cables also, etc. Now, the thing is that these structures are much lighter than all other types of structures because the loads are all axial and they will be designed in such a way that the volume of that material will be minimum to carry those loads. And this is, of course, a great advantage because the transportation cost for materials from Earth to Mars is Earth to Moon or to other structures are very important. Here we are seeing different types of cable-strut structures. We may have towers, we may have bridges, we may have the type of structure here, which may be deployable, which can be deployed so that it can be used very easily, can be carried to there very easily. And this is a dome that can be done using cables and struts. This is another way of using them. So if we have a module made of cables and struts, then we can put one on top of the other. So we may go up and we may have a larger structure using these cables and struts. Now, of course, there are bar structures, there are cable structures, and cable strut structures are both of them. The bar structures, as we know, there are, for example, trusses. For cable structures, we have cable nets, and cable structures are such that They have both elements. Now, but inside them, there is also another type of cable-strut structures, which are tensegrity structures. Tensegrity structures or tensegrities or tensile integrated structures are such that all the connections are made at the nodes, so that between nodes there are not any connection. So tensegrity structures can be considered as a subspace of cable-strut structures. As we have said before, there may be press stressing or not in the cables, and that is very important to have the shape of the structures. The distinction between cable-strut structures and tensegrity structures are considered in various publications. And the thing is that in the struts there are only axial loads in a tensegrity system. In general, there may be, of course, bending, etc., in these struts also. Now, the properties and advantages of these structures are first, listed by Skelton, and then One and Tour. So they are very efficient as far as the material used is considered, because as we had said at the beginning, the design is made at such a manner that they may be deployable. It is a very good advantage because we have to carry them to these long distances. They are easily tunable. We can play with them by changing the press stresses. Their shapes, etc., can be changed. They can be easily modeled, and they can be also smart, because by applying different kinds of actuators, by changing the lengths of the bars, etc., and bars and cables, you can make it a smart structure. They are scalable. That means that they may be in a very small scale, or they may be at a large scale. One of the towers that I have shown at the beginning, that design is for a tower of 2 kilometers high, which shows that it is the scale is not very important. Biological inspired a tensegrity model can be used for defining biological structures also, except these ones, except the last one. It is not important for that purpose. They are very well adapted for space applications, and a history of them also are given in that publication. Now, their analysis is different, is not very easy, because cables, the behavior of cables make them nonlinear. If we consider the stress-strain diagram of materials, there may be linear, if you consider strain at the x-axis and stresses at the y-axis, there may be linear materials, strut or cable. There may be nonlinear ones, and there may be ones which have a ruptured value. So, except the linear ones, then those properties make the structure very nonlinear. Therefore, their analysis is not very easy. With even the known techniques, like finite element method, we will talk about in a few minutes, they cannot be done very easily. Now, there are many techniques that are, put forward for making analysis of them. They start from finite element method, as we will talk about in a few minutes. It is not possible to solve these problems by simple and direct application of finite element method. So, for example, we apply a method called P-delta method, which means that you apply a small amount of force to the structure, it deforms, and then you consider that deformed structure and add another small amount of force. So, by iterations, you go up to the known level of force to solve the system. But we have another technique which we have applied for solving these type of structures. This method gave way to the first total potential optimization method using materialistic algorithms, and then in the second approach that gave way to the method, finite element method with energy minimization. Now I will talk about that method for a few minutes. Now on the left we have the classical finite element method, which is very common to all structural engineers. Now on the right we have the new application, which we call finite element method with energy minimization. Now, the first step is we first of all model the structure. The second step, we divide the structure into finite elements, which have finite dimensions. Then these elements are connected to each other, of course. At the connections, we define nodes so that the deflections and forces are considered to be applied measured and applied at over these nodes. Then we consider shape functions. We find shape functions such that if in that finite element we know the end node deflections, we can calculate the total, the complete shape function of the structure. That enables us to write on the sixth step on the left in finite element method, to write the equilibrium equations between forces acting on the nodes and the displacement that we measure on the nodes. This we do on finite element method. In finite element method with energy minimization, we do a different thing. We have a finite element, but instead of writing the equilibrium equation, we calculate the total potential energy on that element, the strain energy and the work done by the forces. Then in the seventh step, we combine all these things. On the left, we combine the equilibrium equations of finite elements to the total system, so that totally we obtain a matrix equation in the form that a large stiffness matrix multiplied by deflections is equal to the force. On the right, in the finite element method with energy methods, we combine the elements, the energies in finite elements to the whole system, so that at the end we obtain a functional which have the total potential of the system written in terms of forces and deflections. Then the next step, of course, on the left-hand side, if we have a matrix equation, we solve it and we find the deflections, displacements, according to this deflection equation. On the right, we have a functional. We want to make it minimum, so we use an optimization algorithm to find the displacement U that make the total potential minimum. That is, on the left we solve a matrix equation. On the right we have a energy equation, energy optimization. If we find displacements, then all the unknowns of the problem can be solved in the next step 9. Now, this is a flow chart for the problem. We can also define this, we can also show the difference between FEM and FEMM at this page. Now, as we know, the total potential energy of a system can be written, if it is in linear terms, as the first equation in this page. The X transpose AX minus X transpose P is the total potential energy. Now, in FM, actually, this is the real equation that we start with. But if we take the derivative of this equation with respect to X, that this equation is something like AX squared minus PX to be minimized. So if we take its derivative, we find AX is equal to P. So that means that the matrix equation that we use in finite element method is actually, again, obtained by minimizing this function. In FEMM, of course, we have the same total potential energy equation, and we apply a minimization algorithm to find X to make this function minimum. Now, why FEMM is more general than FEM? Because now, if we want to solve the problem by finite element equation method, the matrix A must be invertible. That means its determinant must be equal to 0. Otherwise, we say that the matrix is ill-conditioned and there is no solution. Actually, this is not true. There may be a matrix which is not invertible, but there's still solution. There's still we can find a solution to that problem. Like, for example, after buckling, for example, at buckling, the determinant will be equal to 0, but there is still a solution to the problem, and we can find it by using the finite element method with energy minimization. This functional here, in general, now, if we go back to the original equation, we can write this equation, the first equation, if everything is linear. If anything is not linear, then we cannot write this equation. We will, in that case, be able to write a functional, which is this functional involves geometry, constraints, material properties, forces acting on the structure, displacements, etc. Everything is in there in an implicit way, so that cannot be written in an explicit way. So we can solve these problems by this finite element method with energy minimization. This is a new application. Now, of course, this is for static analysis. For dynamic analysis also, we have other methods to be applied. Now, when we come to the design of these structures, about these structures, we talk about two types of designs. One of them is form finding, because you cannot just arbitrarily connect bars and cables to make a structure. You have to design it in such a way that it will stand by itself. And it is called form finding, finding a form such that the structure will remain as it is. So this is also a difficult problem to solve. You cannot just arbitrarily connect them and make a structure like this one. And there are many methods in the literature for finding the form of these structures. Now, when we come to the design, of course, the sizes of the elements and the press stress that must be used in the structures must be calculated, and this is another step. This is the structural design of the structure. That means that after you make a design of the form of the structure, then there is also a structural design type. Now, here also there is another improvement. Now, there is something like said to be grouping, an important concept in structural design. That means that, for example, if you have structure, then you cannot make it in such a way that everybody is optimum. Every structure, every element is structured. In that case, for example, let us say that in a structure with 20 bars, each bar will have a different dimension, will have a different area. So what we do is, as a designer, we group them. Let us say that we say that 5 of them, we will say 5 of them will be the same dimensions. The next 5, which is, for example, at the upper part of the structure, will have a minimum, we have other dimensions, etc. Now, this can be done also using an automatic grouping technique. Now, the loads, when we come to the design of these structures, of course, there are dead loads. Dead loads, on Moon, for example, of course, they are not as important as on Earth because of the 1/6 acceleration.
Cengiz, 8 minutes.
Okay, so dead loads are less important on Moon, but we have the shielding, so there is the weight of the shielding. Live loads are not very important because, we do not have, high-rise buildings. Moonquake loads are important. And the thing is that on Earth, the earthquake designs are done in such a way that the structure may have some damage, but the human lives will be saved. This is not true on Moon and other space structures. We have to have a structure that will have no damage, whatever the earthquake is. So this is an important difference between load applications. Now, internal pressure, we have seen, very important presentation yesterday about this thing. Because of the internal pressure, the type of the stresses on the structure will be different. Impact loads, we know them. Now, there is a simple calculation here. If, the structure, if on Earth, we have a structure like this, 30 meters square, for example, with some, arbitrary loads, with some given loads, the column will be 750 millimeters square, the area. If we have the same structure there, with the shield loads and with the internal pressure, the minimum area will be 14,000 millimeters square. This is a simple application, but it is, very demonstrative. On Earth, 750 millimeters square. On Moon, 14,000 millimeters square. So it is very important. There are also thermal loads because, we are seeing the sun or not. Everything will be different. The load combinations also. Now, material properties are very important. The transportation cost is important. So, there are many figures given in the literature about this thing. So I asked this morning to the AI assistant of Google, and it gave a figure like $3 million per kilogram. Perhaps it is it's an excessive number, excessive figure. Now, in an application for a lunar very high strut, for a very high tower, then we are seeing that the the material that we are using, the materials that we are using are much stronger than steel. For example, yield stress is 1700 Newton per millimeter square, while for steel, the yield stress is 300 Newton per millimeter square. Now, one more thing, last words. Now, in the literature, when you look to the, artists' things, they say that they give the form of the structures like these ones. But these are not, structurally the best ones when there are internal stresses. The convex structures will be much better than concave structures, actually. The figures on the right will be much more applicable than the ones on the left if we consider the internal stresses. So that's why, for example, on the right, a structure made by cables and struts, as shown here, a deployable one, will be much more applicable as compared to the other ones. Now, these structures are more versatile as compared to all other structural types. They can be used for making habitats, towers, bridges, roofs, for example, or small craters, etc. So they are much more versatile as compared to others, and most effective, as we said, as I have said a few times, because everything can be optimized in these structures. Now, thank you very much. I have a list of references at the end of these presentations. Thank you.
Thank you, Cengiz. Do we have any questions here? It is a couple of minutes. Yeah, Gary Barnard.
Hello. Yes.
Yes.
An excellent presentation. I'd love to see, how this comes together. You'll see in my presentation, a heavy stress on the value of self-supporting, self-sustaining structures, and the notion of your extension really, FEMM, really aligns well with this notion of master equations and the broader analysis of the physics and systems engineering of it. So again, hats off to you on an excellent presentation. I found it very helpful and informative.
Thank you. And really, I'm amazed of the success of the FEMM. I was able to solve many problems using FEMM, which could not be solved by the well-known FEM method. Yes, thank you.
Thank you. And that's, yeah, thank you for an interesting presentation with a pretty new method on to compete with standard fine-hand elements. Sounds good. And
think of it more as a refinement, if you will.
Yeah.
Basically what it comes down to is if you can take two different approaches to a problem and you can show how they relate to one another and one gives you a better answer. Okay, it's not that the other's wrong, it's just, you can, it's sort of the, Archimedes' arrow argument. You can structure a problem that you can't solve very easily. Okay, what's interesting is, can you structure a problem in a way that you can solve it?
Yeah. Non-linear finite elements are always difficult to solve.